So we just want to have a basic understanding of how to construct or find the confidence interval. So remember that when we are dealing with estimation, in fact, the course statistics just deals with estimations. So we talked of the mean of a sample x bar to say x bar will estimate the population parameter mu. Now, why do we use x bar? Why is x bar a good estimator of mu? Remember that the expectance of x bar will give us mu, and as a result we can say it's unbiased. It's an unbiased estimator of the population parameter mu. So this x bar alone is called a point estimate. You just estimate the population mean using x bar. It's a point estimate. But then to increase or to reduce the probability of error, we can come up with what we call a confidence interval that will give us a range of where the population mean falls. So in this video, we'll primarily focus on the population mean. Then in the next one, we'll deal with proportions. So the confidence interval will give you a range of values where the population mean falls. So you look at how the estimator deviates from the true proportions. So that range is that will guide us as we construct our confidence interval. So an overview of how confidence interval should look like: we have our point estimator, which is x bar, the one that we've estimated. Then we look at the deviation about the mean, how the mean or the estimator drifts away from the population, from the true population mean. So we will call that drifting number or range as our error. So the deviation from the mean is what is known as our standard error. So we can have our point estimate to be more or less than the true population mean. So add the error, which is depending on the sample size that we're dealing with. So you have the one which will be greater than 30 and the other one which is less than 30. So every time you have a sample which is more than 30, it's recommended that we use a standard normal table. So which is v alpha over 2 times the standard error, which is the sample standard deviation divided by the root of the sample size. But in a case where we have our sample size to be less than 30, so this is where our sample size is greater than or equal to 30. But in a case where we have our sample size being less than 30, then we bring in the student distribution. The student distribution is the one which we're going to use for our sample size which is less than 30. The one which was developed by W.S. Cossette, which is commonly known as the t-distribution now. So when constructing these intervals, you need to have both tables, the standard normal table and the t-distribution table, where you're going to find. So our n minus 1 here represents the degrees of freedom, which is commonly denoted by the letter v. So you can write this as x bar plus or minus t alpha over 2, then you've got your v. Your v is your degrees of freedom. So the question I'm sure that may arise here is that why are we dealing with alpha minus 2? In fact, what is alpha? So let us understand this. So I'll take you back to the normal distribution curve. So I'll roughly like draw it so that we have a basic understanding of what we're dealing with. This is our standard normal distribution table, and the probability is found by the area under the graph. So now when we talk of a interval, we're talking of a range of values. So we can have a point from A to B. So if we say that our confidence interval ranges from here, it means our true population mean will fall within these values. and you have your mean here, remember, from the normal distribution table. So from here to here, it shows how the estimator deviates from the mean, even this side. So you've got a range of deviations. So each of the deviation is what is being shown in this range. So the estimator might be more or less than the true population mean, but you're going to have a standard probability of the error of deviating from the mean. Now we want the area away from this range to be equal to alpha. We want everything outside this range to be equal to alpha. So alpha is the acceptance error that we accept, or the error, the probability error that our confidence interval might drift away from. So having this area under the graph, we want the area outside here to be alpha. No wonder we say this part here, the area here, will be alpha over 2, meaning also this side will be alpha over 2. So this is similar to this, just to get us to understand exactly what we're talking about. If we had this to be alpha, of course this represents alpha, but for us to make sure that the entire area outside the range is alpha, we will put it into half, because in fact the fact that we're dealing with an interval, you know that we're dealing with two sides. In other terms, you can say this is a two-tailed thing that we're dealing with. So no wonder we have our alpha over 2 here. All right, so now we will look at some examples that will help us understand or construct a confidence interval. Let's take a look at this one. It says a sample of 10 measurements of a diameter of a sphere gave a mean of 4.38 inches. So already you know that they've given us that this mean is from a sample, meaning it's an estimate. So we have our x bar being represented by the mean of a sample, which is 4.38. We are collecting the data here, 4.38, sorry, not 4.838 inches, and the standard deviation. So a standard deviation of a sample is denoted with a letter S, which is equals to 0.06 inches. Then we are told to say we have to find the 95% confidence limits or interval for the actual diameter. Well, this is a direct thing. So our n, which is our sample size, is 10. Remember what we talked about to say when we're dealing with a sample size which is less than 10, then we'll go back to the t-distribution table. So that's what we're going to use, the t-distribution. This will give us the actual, or it will be precise in terms of the range where the true population mean falls. So we have our x bar, remember x bar plus or minus, so we have t alpha over 2v, then we have s over the root of n as our general, you can even create a general formula. So we just have to substitute the values that we have. So we have 4.38 plus or minus, then we find this. So we're told to find a 95% confidence interval. So that 95% confidence interval, we need, from there we need to find our level of significance. So our level of significance is represented by our alpha, the one that we talked about. So alpha will come from 1. So I think the easiest thing to do when you have such a question where you're given to construct a confidence interval, let's say 95, which is given in 2%, you can divide that by 100. So you say 95 divided by 100, which will give you 0.95. Then 1 minus the answer that we found, 0.95, will give us our alpha. So our alpha will be our level of significance. So say 1 minus 0.95, that will give us 0.05. So our alpha in this case is 0.05. Now that we have our alpha, since we are finding alpha over 2, we'll divide this by 2 to get, so 0.05 divided by 2, we have 0.025. So we have got t 0.025. Then our degrees of freedom is n minus 1. In this case, our n is 10. So 10 minus 1 will give us 9. Then we go on our t distribution table and find what our t value is. Alright, so our t alpha over 2 over v. So if you are not familiar on how to read the t distribution table, I'll drop a link in the description which will help you to see how you can find the values here. So you're going to find 2.262 from the t distribution table. So this 2.262, you write it here where there's the t alpha over 2 comma v. Right, yeah. Then we multiply with so the standard deviation of the sample has been given to be 0.06. Then we'll also divide by the square root of our n, which is 10 as our sample size. So this is how we find our confidence interval. Then whatever is remaining here is for us to simplify the given figures. Right, so when we simplify this, we're going to get what we call our marginal error, which is this one. So meaning our estimated mean might be more from the true population mean by this or less by this. But what we know is that the true population mean will fall within this range. So we can add this to our point estimate of the mean. So when we add, we get 4.4229. Yeah. Then when we subtract, we get 4.3371. Yeah, so it means our true population mean will lie within this range. Let's look at a different question which we might use our z table. Right, so in this case, we want to use our z our standard normal distribution table. Alright, so the question says Trade King's company is considering opening a new store at a certain location, but wants to know if average weekly sales will reach 250,000. Trade Kings estimates weekly gross sales at a nearby store of 40 samples and arrive at already. From the statement before we finish, we've been told to say our sample size is 40. So the fact that our sample size is more than 30, we use our z-score. Alright, so 40 samples and arrive at a sample mean of 263,590. So our sample mean, that's our point estimate, we've been given to say it's 2,063,590. Right, so the standard deviation of the sample is 42,000. So that's our S, 42,000. Then construct a 90% confidence interval. So first thing first, what is our level of significance, our alpha? So we'll say 90 divided by 100, then we'll subtract that number from 1. So when we subtract, we've got 0.9. So 1 minus 0.9 is 0.1. This is our level of significance. So it's remember the general formula we talked about is x bar plus or minus z alpha over 2, then we have s over the root of n. So our x bar we've been given to be 263,590 plus or minus. So our z alpha over 2, we will divide the alpha that we've been given by 2. So we are finding z corresponding to 0. So this is the area that we have, 0.05. Then we find the z-score corresponding to this area. Right, so when we use our z distribution table, again, if you're not familiar on how to use the z distribution table, I'll drop the link in the description, then you can check it out. This will give me 1.645. Then I can substitute whatever values I have. So I have 1.645, then my S there is 42,000 over the square root of n, which is 40. Then from there you can now simplify the values that you have. So basically you simplify this, and okay, let's do it so that we find the marginal error, then add and subtract from our point estimate. Yeah, so this will be our marginal error, 10,924.08. So you can add to the point estimator and also subtract to get our confidence interval. Alright, so this has been a very quick video. In the next one will also be quick and look at proportions. So remember to subscribe and hit the notification button to get the latest videos on statistics and